I've been meaning to get back to this series for some time, and a bit of orange reminded me why. So let's talk about radiometric dating. This period of instruction is a bit different. For one, we're not on the Nexus. We are at Mount Vesuvius in Italy, the volcano that wiped out the cities of Pompeii and Herculaneum in 79 AD. I'll also be including a clip from one of A Bit of Orange's videos which highlights some key misconceptions on this topic. Somehow, I'm instructing a science teacher on something he should know if he's teaching science, but as we've seen before, he needs it. There's one more thing I need to say before we get to the 40-second or so clip I'm using from his video, a section called The Takeaway. The fact that he has told me he is a science teacher is absolutely infuriating. I have no doubt that he is lying to whole classrooms of students because the curriculum he is supposed to be teaching directly refutes a literal interpretation of mythology. As far as I'm concerned, any teacher that censors or alters the lessons in science textbooks, which are written to educate and teach factually accurate information, should have their employment terminated, especially if you don't have an understanding of the topic at the level you're supposed to be teaching, because you can't teach a subject if you don't know anything about it yourself. With that out of the way, we'll play the whole clip and we'll start instructing Orange on this entire thing.
How does evolution determine the age of a fossil? Well, if you have a fossil that's found in 300 million year old rock, clearly you have a 300 million year old fossil. But how do we know that the rock is 300 million years old? Well, because it contains a fossil that's 300 million years old. So the rocks date the fossils, but the fossils date the rocks, which date the fossils that date the rocks. Are you getting dizzy yet? Deep time is not based on scientific observation. It's based on assumptions and circular reasoning, wherein evolution is used as evidence for evolution.
So with this clip alone, we have to cover a few things, Orange. First is, of course, that evolution, as in the theory of evolution, doesn't determine the age of fossils. Geologists do, via methods we will talk about more in a moment. First, we need to talk about this misconception of circularity. As I stated in your comments, you're confusing relative dating with absolute dating. Since we all know we are dealing with a chunk of time here, let's try this analogy. Let's view all of geologic history, the entirety of the geologic column, as the face of a standard clock, with 12 being the beginning of the Cambrian for simplicity, and each subsequent hour being roughly analogous to a specific period in geologic history. That would make 1 the beginning of the Ordovician, 2 would contain the Silurian, 3 the Devonian, and so on. As you should know, Orange, each period has index fossils, which are only found in that block of time. So if you find a trilobite that looks like this, you know you're dealing with strata that is from the Cambrian period. While if you come across an ammonite like this one, you know you're looking at strata from the Jurassic period. This is relative dating at work, using index fossils to determine a very broad range of time. We didn't know the ages of these strata like we do now when the geologic column was devised. Estimates had been made, but no one in mainstream geology was arguing for an Earth that was only 6,000 years old, and even conservative estimates put these periods at millions of years old, orders of magnitude beyond what you think. Some things never change, I guess. This is where absolute dating with radiometric isotopes comes into the picture. We discovered radiation when we noticed that certain materials were noticeably warmer than the other materials around them. At first, this was simply a strange curiosity, but as we developed better testing methods, we found out why they were warm. The expulsion of energetic particles, mostly alpha and beta, which don't actually penetrate the skin and can be simply washed off with soap and water as a decontamination measure. Because radiation doesn't give you superpowers. Some materials do shed higher forms of energy like gamma rays, which can go through you without issue and require lead or several feet of everyday material to stop. Anyway, through further study, we discovered that these materials were decaying into lighter elements that are more stable and either don't radiate energy or do so at a less frequent rate. Now, we know that a sample of these materials, say a 1 centimeter cube of uranium, for example, will shed these energetic particles and wavelengths a certain number of times on average in the space of, say, 1 minute. It's an average because we can't predict when an individual atom will decay, let alone what atom it will be in a given block of material. But given a specific sample size, we can get a pretty good idea. Kind of like trying to measure something to exactly 40 inches, there is going to be some leeway there that's only detectable with a feeler gauge or a micrometer. So relative dating has gotten us to a large block of geologic time, or hour, in our clock example. Radiometric dating with known decay rates of the isotopes used, like potassium argon, for example, get us to a more precise time frame of, say, 1 to 2 minutes, for example. When dating the strata, we use several different isotopes, not only to give us a range based on different decay rates, but to provide cross-corroboration for accuracy. And because of that, some isotopes are only useful in a certain date range. As an example, you will never see carbon dating used on Mesozoic era fossils. That particular isotope only ranges out to about 50,000 years, at which point it has decayed below detection thresholds. We use other isotopes for that, which can clock back much further. There is no problem with circularity here, Orange. You just don't know the difference between relative and absolute dating, and should probably be a student instead of a teacher. Now for some arguments I often hear against radiometric dating, the first of which is the assertion that we don't know the initial condition. While, as with everything, there is a margin of error, it's not like we don't have a good reason to have the estimates that we do. We also aren't pulling these estimates out of the ether. I'm going to stick to potassium argon as an example because the methods for determining the original amounts of things like uranium are a bit complicated for a basic primer on this subject. Now, argon is one of those things that's expelled in a volcanic eruption and can be caught in the cooling and solidifying magma, but it works its way out during that process since it is a gas. Potassium, however, doesn't have that luxury and is trapped within. There is one more analogy I need to use before we move on. See, even though newly formed igneous rock is cooled, there's still a lot going on there chemically, and it hasn't actually stabilized. So you can't take a fresh sample from an eruption that just happened and date it accurately. Think of it as an adhesive, like cyanacrylate, otherwise known as superglue. When you use superglue, it forms a bond very quickly, but put it under any real strain and that bond will break. Adhesives have two different timescales that they use. The first is the bond time, which is what's needed to have a passable hold. The second is the cure time, the time needed for the bond to be solidified, for everything happening chemically to stop. You may have a basic bond, but the chemical reactions are still going on, and until they are done, the process is still ongoing. It's kind of like that with newly formed igneous rock. It's solid, sure, but there's a lot going on chemically because it hasn't cured yet, for lack of a better term. Once it does, we can get a solid and accurate reading on it. The cure time for igneous rock is unfortunately several decades. Now, this is often a point of contention because if we need to wait so long to get an accurate reading, how do we know it's accurate? That's one of the reasons we are at Vesuvius today. Remember when I said that when this thing blew, it wiped 2 cities off the map? It also affected several other cities in the area and was very well documented. We know from a historical standpoint when it blew. When we date the material in question, it comes back as a match with a reasonable margin of error, as having happened when the historical records of the event say. But how do we know that? Well, all radioactive materials decay into lighter and more stable materials, like I said. They are all in an unbalanced and unstable state, and as a result shed particles to reach stability at some point. They all decay at different rates as well. What you're seeing now is a block of uranium in a cloud chamber, courtesy of Kyle Hill. You're seeing in the vapor energetic particles interacting with and disturbing the vapor. This is happening in a 360-degree sphere and is not limited to the two-dimensional plane we are seeing now. As these particles are shed, individual atoms are becoming stable, lighter elements, which in this case is uranium making its way to lead. It is in this same way that potassium decays into argon. But not all potassium is radioactive. Only certain isotopes of elements are radioactive. I realize I've been using that word and haven't defined it yet. That's okay because we need to do that here anyway. An isotope is essentially a heavy version of a particular element. It has the same number of protons, but not the same number of neutrons in the nuclei, which is what makes them unstable and thus radioactive. What we do is measure the ratio of the radioactive element against the presence of the daughter element, as in what the radioactive substance decays into. That ratio will give us a time frame for the age of the material. Radioactive isotopes have what's called a half-life, which is the amount of time needed for half of the radioactive material to decay into the daughter element. Half the original material is still there and hasn't decayed yet, though. That material goes through a half-life of its own, going from 1/2 to 1/4 to 1/8 to 1/16 and 1/32 and so on, till the radioactive material is no longer detectable. Again, these materials decay at different speeds, some of which decay slower than others and thus last longer and are able to help us clock back further than others. For example, carbon-14 is only usable out to about 50,000 years, while something like rubidium-strontium is usable out to a few billion. The decay rates, by all indications, are constant and are the same no matter what time frame, which is another objection I see for radiometric dating. The issue here is what is known as the heat problem. See, some people don't subscribe to uniformitarianism, which is the position that natural processes like radioactivity are the same today as they were in the past. By all indications, this is the case. Decay rates are remeasured on a regular basis to try to get more precise measurements. If decay rates were different in the past, as in they decayed faster, we would have a couple of issues. The first of which is that radioactive decay creates heat, so the planet would have been substantially hotter and uninhabitable for longer if the decay rates were faster. Remember that some of these materials clock back billions of years, and for us to get the readings we get today, with the idea of the Earth being 6,000 years old, the Earth would have been a literal hellscape, and it would have been evidenced in the geologic column. The second option, for those who reject uniformitarianism, is that whatever creative being is invoked would have deliberately set up these materials to give the illusion that the Earth is approximately 4.5 billion years old, and that the layers of strata we date with these methods only appear to be millions or billions of years old. That would be deceptive, and not at all what we would expect from a God that is not supposed to be the author of confusion. So to recap, there is a difference between relative and absolute dating, and despite what Orange and others may say, there is no problem of circularity. So when he said,
So the rocks date the fossils, but the fossils date the rocks,
he was, as a science teacher, inexcusably wrong. Radioactive isotopes used in absolute dating of the associated strata have constant decay rates, and if they were as radically different as they would need to be to give the illusion of an old and absolutely ancient Earth, then we would see evidence of that in the geologic column. Either that or whatever creator was invoked would have been deliberately deceptive. Finally, because the decay rates are constant, once the material we want to date stabilizes chemically, we have modern historical examples that were very well documented, which allow us to have sources for corroboration to confirm the accuracy. With that, this concludes your period of instruction. Your next period of instruction will be in the dirt as well, as we look at how the layers of the geologic column are formed, how fossils are formed, and talk about Dr. Mary Schweitzer's work on soft tissue found in said fossils.